talk today. So just a quick reminder before we started, you are always looking for speakers. So if you know someone or if yourself wants to give a talk on the ACEAS, future ACEAS seminar, or maybe you have someone visiting your institution and you want to hook them up to give a talk, please let the committee know. And today you're going to have Dr. Marina Azaneu talk about the influences of shelf break process on the transport of warm waters onto the eastern Amundsen Sea continental shelf. So Marina is an oceanographer from South Brazil. And the fun fact is Marina and I graduated together in 2010, South Brazil. And she's also completed a PhD at the University of East Anglia under the supervision of Karen Haywood, where she has been involved in observational campaigns in the Amundsen Sea and Weddell Sea, deploying gliders and moorings to try to understand the ocean variability role on the ocean heat transport towards the Antarctic ice shelves. So let's welcome Marina.
Thank you very much for coming to see. It's a Friday afternoon, so it's pretty nice. It's quite nice to come here and present this work. It's something that I did part of my PhD, part after when I was in the UK, and then I published this last year. And a lot of work has also been done here at this university with this theme. So it's quite nice to be here, and yeah, it's nice to talk about it. So this work was done at UEA and when working with Ben Weber and Karen Haywood. I'm trying to skip. Okay, cool. So I'm pretty sure that my audience knows about changes in Antarctica and mass loss around Antarctica. But just to give like the overall idea, Antarctica is going through a lot of ice mass loss, particularly in the Western Antarctica. This has been associated with ice shelf thinning, and the thinning of these ice shelves is mostly associated with ocean-induced basal melting, right? Particularly in the Western Antarctica, in the Amundsen Sea is one of these main regions. This heat that is transported over the shelf that ultimately will lead to the basal melting of these ice shelves is transported through the Circumpolar Deep Water. This is the main driver of this heat. And the way this water mass reaches the inner continental shelf, is through these two, when we are talking about Eastern Amundsen Sea, is through the central and the eastern troughs here. Is the main pathway that these warm waters reach the inner shelf in Amundsen Sea. So when we talk about ice shelf basal melting and the amount of heat that reaches the ice cavities, some of the proxies that we use for this amount of heat is the thermocline depth over the shelf and the temperature that is there, above this thermocline that is in contact with this subcavity. This thermocline depth, this amount of heat, is going to be influenced by many factors. And so like buoyancy loss and all these things that are happening on shelf. But the amount of heat that is going to reach this inner shelf is also influenced a lot by the long slope current system, particularly the undercurrent. So when we're going to talk a little bit later about the circulation in the area, we have normally a westward flow over the slope, and then an eastward along slope that we call the undercurrent. And a lot of studies connect the strength of this undercurrent with this flow onto the shelf. So it's we believe that it's basically the interaction of this eastward undercurrent with the shelf break troughs that are gonna facilitate the flow of the circumpolar deep water onto the shelf. And thinking about the variability, the winds, they are a big factor. They are gonna be influencing the conditions over the shelf. So in terms of the buoyancy fluxes and up and down of the thermocline, but they're also gonna influence the dynamics of the slope currents over the slope. And this is like the changes in this undercurrent and as a dynamic response to the change in the winds is a big factor impacting this onshore heat transport. And it's also one of the big uncertainties that we have on those areas, on like how is the variability of this flow and how the dynamic works and those sort of things. So what I tried to do in this work was to investigate this slope current system, the variability of this system and of the heat that is transported through the Pine Island-Thwaites, the central and the eastern troughs. And for that, I used data from 5 moorings. So in this presentation, after I present the data, I will give an overview of the circulation that we have on this the vicinity of the shelf break using like snapshots from CTDs and ADCPs. And then I will talk a bit about the variability of the moorings observed in the mooring observations, and then the mechanisms that are driving this temporal variability. So in terms of the water mass distributions, and then the influence of these local winds. And I hope you guys get out of this talk with 3 main points, which are that the zonal wind stress is what drives different CDW varieties onto the eastern Amundsen Sea continental shelf. That the heat content onshore flow co-vary strongly between the central and the eastern troughs, that there is a dynamical link between these troughs, and that the El Nino from 2015 to 2016 led to a really strong onshore heat flux in this region. So to talk a little bit about the data I was using, as I said, I had many CTD stations. So we had 3 zonal sections, so meridional section 1 and 2, which are in the central trough, this area, and then meridional section 3, which is in the eastern trough. And we have 2 zonal sections. So this one's the 5 central trough, and then this is the 6 eastern trough. These are the CTD stations, and then I'm zooming in the central trough and the eastern trough to show where we had the moorings. So we had these 3 moorings in the central trough. So M1, M4, and M5. There are the 3 they were sampling between 2012 and 2014. And then here, co-located with M1, I had M12, which sampled between 2014 and 2016. The same period that I had this other mooring, M20, on the eastern trough. And with this data, I estimated daily heat flux time series. And I say heat flux because it's basically heat transport, but I'm not integrating in an area because I have just the mooring, just the measurement in that point. So I'm integrating velocity and temperature just in depth. So that's why I call it heat flux. And I used, for the velocities, I used a rotated coordinate system. So my velocities were rotated in a new coordinate system that is either along the trough component. So let's say for each trough, I get the trough main direction and I rotate towards that direction in a way that positive values mean onshore along the trough. And I have the along slope component that is basically along the direction of the slope. That won't matter, that component won't matter that much for most of the moorings, but it definitely matters for this one, the M5, because it is located at the shelf break over the upper slope. So the along slope is kind of the most important flux for me. And then I look as well at the 2 different components. So the heat flux that is driven by variations in temperature and the heat flux that is driven by variation in velocity. So just to highlight here, because ME1 and ME12 are co-located, we have in total 4 years of measurements at that point in the central trough. So here I'm putting basically the temperature and the velocity sections. Here, these 2 meridional ones are the central and the eastern trough. And then the temperature and velocity for the central trough here, the zonal section, so we can have an idea of the circulation. So in this area, when we look at the slope, we are going to have the westward surface intensified flow, and then the eastward subsurface intensified flow on both meridional sections. So this is basically the undercurrent that I was talking about, that is kind of a persistent feature and has been shown in modeling studies and everything. And we see it here in our sections. And when we look at the moorings, as I said before, mooring M5, this arrow here is basically the average velocity for that mooring for the whole period. And we can see that has like a southeastward direction. So most of the time, this mooring was capturing this like cyclonic flow entering the trough. And when we in here on the zonal section, we see that we have the onshore flow on the eastern side and the offshore flow of the warm waters or modified circumpolar deep water. So the waters that are already modified onshore, they get out of the shore on the western side. So when we look at the moorings, the M1 and M12 were capturing this like onshore flow, and then the M4 was capturing the offshore flow. And then on the eastern section, the M12, M20, the average flow does not align perfectly with the trough. But when we look at the time series, it was most of the time capturing the onshore flow. It was just a bit too far off. So it was getting like the flow turning cyclonically and entering. So when I'm thinking about the variability of the heat flux, because the heat flux, as I said before, is going to be the predictor for basal melt, right? So the import of CDW to the shelf is associated with the heat flux that is important. And the heat flux is going to depend on temperature and velocity, but changes in temperature and thermocline depth will greatly affect heat content. So when I look at changes in heat content and changes in velocity, that can give me insights on the dynamics that are leading to the change in the heat flux. So that's why when in this figure here, I have basically on the top, I'm showing the heat fluxes. So I have the heat flux for the colors show each one of the moorings that I was talking about. This is basically the along trough heat flux. So whatever is positive is the flow going onshore. And just the green one that is along the slope for the slope mooring. But let's focus on the other ones. And then on the bottom panel, I have the heat content variations. And on the bottom is velocity. So I'm looking at these different components so I can understand what the hell is happening with the heat flux. And what we see is that we have interannual variability in velocity. And we have interannual variabilities in heat content, but they differ, right? So between 2012 and 2014, we have no like consistent variation in their long trough velocities, while in the heat content, we have this like steadily decrease in heat content. When we go for 2014, 2016, we have changes in velocity that are basically the opposite of the changes that we see in heat content, in a way that the stronger velocities are related to the lowest amount of heat content, and they're actually negatively correlated. So when we look at the combination of these two factors, which leads to variations in the heat flux, I see that the greatest correlation I find between the heat flux and its components is with the velocity varying component of the heat flux. So it's more than 0.9 for all the moorings. And that is like, that is kind of consistent. We can see this increase in velocity and the increase in the heat flux in this period, right? So we can say that the long trough heat flux variability is primarily driven by velocity. This is something that has been shown already in other studies, and we see this clearly here. And we can see as well, together with this, the time series, that velocity was the dominant driver for this increase that we observed in the heat flux during these last 2 years. We also found that when I correlate the heat flux between all the moorings, I also see that the highest correlation happens between the central and the eastern troughs. which are the M12 and M20 during this period. They are the highest correlation. So this suggests to us that we have a covariability between central and eastern troughs that is dictated by current dynamics. So this supports the idea that we have a dynamical link between these two troughs. And when we talk about a dynamical link, and we think about like a larger scale forcing, then normally we talk about, we think about winds. Like normally the winds are the forcing that can connect these regions dynamically. This already is quite an interesting point because a lot of studies talk about different responses, like a heterogeneous response across shelf for these troughs in relation to forcing. And here we are showing that we actually have like a coherent response between these two troughs. And then I was like, okay, we see that, but we see the heat content was changing differently from what I was expecting. Normally we think about increasing flow of CDW with increasing temperature. That's not what we're seeing. So let's look at the moorings in the water mass variability. And what we see here, this is basically temperature for the mooring at the central trough. What we see is basically two periods in which we see this like warm inflow of waters together with very shallow thermoclines. And then we have the deepening and cooling of these waters. Then warm, again, shallow thermocline during spring, and then steady decrease and cooling for summer, and then until we reach these very minimum temperatures by the end of 16. And that's quite interesting. That is pretty different from what we were expecting in terms of because we saw in that period an increase on the flow. And interestingly, that is the same that we observe in the other moorings as well. Even when we are the upper slope, that is the mooring M5, I forgot to mention, but these are the velocities. So these are the velocities being the y-axis aligned with the along trough. So whatever is here means onshore. And I know there are some people working with eddies on the shelf break here, and there's a lot of cool stuff happening here. But anyway, so we see on these moorings the same behavior of very hot, warm waters, shallow thermoclines, and then cooling after in all the moorings that we see. So in the upper slope and the eastern trough and the central trough, which give us this idea of this coherent temporal variability across the central trough, and that is also consistent with the eastern trough. And that suggests that these changes are part of this like larger spatial scale variability. But these changes, like in the thermocline depth and so on, they can be led by like heaving of the isopycnals. They can be led by like remote changes. There are many things that can lead to these changes. So I went to the basics and I went to the TS diagram. And in this TS diagram, basically, this is like the M5, the upper slope mooring. And I got the section, the CTD section that is cross slope. And I plot here in gray the CTD stations that were more offshore, and in purple, the CTD stations that are onshore. And then the different markers, they give us different depths, and the colors are according to time. So when we look at the beginning of my time series, we can see that like the reddish dots, they're all going over the waters that are more onshore characteristics. And as we move along time, when we go towards like the colder period and the deeper thermocline, we get waters that are more aligned with the shelf water properties. So they both get cooler. However, we see a diverging behavior between shallow and deep waters. So we can see that while the more shallow properties, they become less dense, the waters at depth that become more dense. So they have a divergent behavior in terms of density. And so what was happening when we look at this cross section, we can see, and we look at the depths that we are looking at, we can see that if this was moving, shifting offshore and onshore, that's basically the behavior I would see, right? So in the shallower waters, I would see waters getting colder and lighter. And the deeper waters, I would see waters getting colder and denser. So that would be the behavior I would see if this whole system was moving forwards and offshore and onshore. So the changes we see in these properties are very likely related to this shift in the meridional gradients of temperature, salinity, and so on. And that is consistent with this diverging behavior and density. So basically, when we go back to our time series, what we think is that when we have this cold warm period, we have this whole system, the Antarctic slope front, and this warm deep water core moving onshore. And then when we have this the cold periods, basically this whole system moving offshore, this warm waters going offshore, and then this colder, denser waters moving upwards in the bottom magma layer. And so to have this whole, so this brings us again to this idea that I see this whole frontal system moving offshore and onshore on both central and eastern troughs. So this brings us again the idea of this dynamical link of this whole thing moving, and not like if you see one mooring changing, we can think, oh, it's the current that entered and moving to one side or the other side in the trough. But no, it's something that is coherent. So we go again to the idea of this big dynamical link and this forcing. So I went back to the winds and how the winds work. What are the mechanisms that were leading to these changes? So I looked at the zonal wind stress and to the wind stress curl. And basically this map is just an example. What I'm here is a correlation between the central trough, a long trough heat flux with the winds, in this case, the eastward wind stress at each point on this map. And here is the eastward wind stress with the onshore flow at the eastern trough. And basically we have positive correlations all over the place, and the highest correlations above 0.45, they're in these regions which are kind of similar between the two moorings. And we saw that for all moorings, except for the upper slope one, the main correlation, the main driver, let's say, would be the eastward zonal wind stress and not the wind stress curl. So I got these two areas where we have the highest correlations, and I created one time series averaging in this area. And then I correlated with my heat fluxes. And with all the heat fluxes of all the moorings. And obviously, but we, as expected, we got that M12 and M20, which are the central and eastern heat fluxes between this period. They had the highest correlation with the eastward heat wind stress, which again brings this idea of this strong relationship between the local winds and the onshore heat flow at both central and eastern troughs between 2014 2016. So we have this kind of dynamic response to these large and persistent changes in the zonal winds. And then just kind of, this is just a time series correlation. So I just went forwards and I did a wavelet coherence analysis, where we can see basically during our time series at which periods this time series have a higher coherence. And we can see that for both central and eastern troughs, when we have periods longer than 90 days, so like 3 months, is when we have this higher coherence between these two, between the winds and this heat fluxes. So this brings to us this idea of this important role the local wind has as drivers of the variability of this onshore heat flux on both the central and the eastern troughs at this like intermonthly to potentially longer time scales. And then and this is supported. I didn't highlight before, but in this the heat flux time series that I had shown before, I had also plotted the eastward wind stress here. So we can see that they all the increase in this period, and as we had the increase in the heat flux, we had the increase in the eastward heat stress together. So all these correlations, the coherence analysis, they are supported by this simultaneous coincident increase on both. And that's quite obvious when I have here is the cumulative sum of the anomalies of both the heat flux and the winds, and we can see how they increase together. Is quite nice. So this increase that we observe in the winds in the eastward wind stress is consistent with the local response that we had during the El Nino between 2015 and 16. And so they support each other. So this connection, this hypothesis that there is a connection between the tropical atmospheric anomalies and the local winds and warm waters intrusions in the Amundsen Sea, this has been shown or suggested by by a few studies, including from Maurice that published this year, and he didn't cite me, by the way, which I think is not acceptable. But these are all modeling studies, and they show that relation. But these studies, they talk about many ways that we have this link, like the link itself, the dynamics through which the winds lead to this increase in these changes. Each study talk about a different way. So some of them talk about just basically the Ekman transport, and some of them talk about many different dynamics to connect that. But those explanations are not really fit with what we are seeing, because normally we expect the stronger inflow of CDW with warmer waters and things like this. So that's not what we're seeing. But in any way, like this is this link we have seen, but this is like the first observational evidence that we have at both troughs, a simultaneous dynamic response to this local and this remote forcing. But then we had to still explain why we had a decrease in heat content and so on. So the hypothesis we had was that these anomalous wind forcing affected the onshore flow through the mechanisms that were proposed by Walling and Dotto. And these mechanisms basically say that the eastward wind anomalies led to the meridional sea surface slope, right? Which then led to a barotropic acceleration of the undercurrent. So if this slope, this undercurrent responded barotropically, intensified, and then the intensification of the undercurrent led to uplifting of this isopycnos through bottom Ekman dynamics. And that leads to the increase in the density in the deep mooring records that we showed here. However, like these studies, they were done on the western side of the Amundsen Sea, and they were showing like warming of the bottom of the shelf, right, with these mechanisms, which we don't see. So the explanation for that would be that in this region, the Dodson Jets trough, which is where these studies were done, there's a difference in the bathymetry of the western troughs and of the troughs that we are studying here on the eastern Amundsen Sea. So in the area, the trough itself is shallower in a way that the warm core of the Circumpolar Deep Water does not reach the shelf all the time. It reaches in episodic periods. And so when we had the uplifting of these isopycnos, we had the inflow of these warmer waters onto the shelf. And then we see a greater flow when we see greater temperature. But when we go to the central and eastern troughs where we are, the shelf is deeper, which means that the warm core of the Circumpolar Deep Water has permanent access to the shelf. It is there all the time. So when I have an uplifting of these isopycnos, what I'm getting is actually a colder variety of the CDW reaching this area. So I'm getting a greater flow of CDW, but I'm getting a colder variety of it. And that's why I end up having a kind of colder temperatures. And these supports as well studies that have shown that we have regional differences in the strength and the response of this West Antarctic ice sheet to answer, because these regionalities will bring different responses. we don't have, during this period, 2014 and 16, we don't have measurements of the undercurrent, right? So I cannot say for sure, yes, the undercurrent was stronger. I can't. But we proposed that based on this all other ideas that we see, like this whole behavior that hydrography, everything gave us. So we saw that in all of the moorings, we saw that this variation between offshore and onshore water masses. We saw these changes associated with the winds, the change in the current. So all of that gives us this support that this is kind of what was happening in that period. And so we can say that, under these anomalous forcing conditions of the El Nino, with this increase of the eastward wind stress, we see this increase in the onshore heat flux that coincides with this colder deep layer and lower heat content with both the central and eastern troughs. So all of this gave us this idea that was happening. And that also told us that at the shelf break, the heat flux rather than the heat content or the thermocline depth should be used as a proxy for the heat content that is going to be over the shelf. Because many studies have used just the heat content or just the thermocline. And for the shelf break, that's not enough. We need the information on the currents, we need the information of the dynamics there as well. And when we talk about 2012 and 14, we see the changes in the heat content, but we don't see significant changes in the heat flux. So our whole hypothesis works for these extreme situations on the 14-16, but doesn't apply here. But these changes in the heat content in this period, they can be associated with like upwelling dynamics or the cyclonic wind stress curl as well, because something that I haven't commented before is that the long slope heat flux is the only one that is more correlated with the wind curl, different than the other moorings. So, and then we also have remote changes in the ocean properties. So the strength of the gyre and everything, all of that could be leading to changes in the heat content in this period that are not necessarily associated with the change in the undercurrent strength. So just to give these final ideas, what matters in the end, which I mean is like, okay, I saw the heat content decreasing, I saw the increase in velocities, I saw the increase in heat flux, but what should I care more, right? And what I believe is that the increase in the heat flux, even though we had like lower heat content and so on, the increase in the heat flux during this period, 15-16, leads to like an accumulative response, right? So the heat is going to lead to warmer conditions on shelf cumulatively. And that is consistent with the unprecedented retreat that we observed in the Antarctic sea ice spring 2016. So even though we had lower heat content, the increase in the heat flux led to warmer conditions at the end of it, So when we talk about the shelf break, the heat flux is going to be more important for us to look at than the heat content or the thermocline depth to ultimately determine what the ice shelf melting is going to be. And the link that we see between ANSO and ice shelf melt that we've seen, from other studies, they're not via changes in the heat content as we believed before, as we suggested before, just the depth of the isopycnal, but mainly via changes in the onshore heat flux, which highlight the need for us to a deeper understanding of the mechanisms of this undercurrent strengthening and so on. And we also think that the understanding and the monitoring of this onshore heat flux is critical, particularly when we have like the prediction of the increase in El Nino events and the shift in the winds as well, which is also going to affect these dynamics. And so was the importance of measuring this, measuring and simulating as well this currents on the shelf break, not just temperature. And very importantly as well, this dynamic response to the surface wind, they differ between like across the Amundsen Sea. And that's very important to be able to, like, these regional differences are very important for us to accurately represent in our models because it's going to have different consequences. So yeah, thank you. This study was published last year. And then I moved here and I started working with something completely different. I'm still working with frontal system. I'm not going to talk about science, but basically now I'm working in a way more tropical environment, but still with frontal structures, frontal zones. So if anyone has any question about my tropical work or my polar work, yeah, that's it. Thank you.
Thanks, Marina. I guess we're gonna start taking questions from the room first. If anyone has a question
Any question?
or chickens.
I sort of have a question.
Sort of.
Yeah. What's it like, the difference between doing this Antarctic stuff and going to the EAC? Which one do you like more?
Oh, completely different dynamics. It's crazy. I have to adjust my mind and understand that, yeah, that 20-something temperature is fine. It's a bit tricky. It is challenging. The dynamics are very different, but I enjoy changing subjects. I do like it. And field campaigns make it all very interesting as well. It's good to not be in cold waters. But yeah, but it's a whole different environment, and it's very interesting to see how the ocean behaves so differently. You know, in the dynamics that I'm looking at, they are very different temporally and spatially as well. So it is cool to change. It's not my first tropical study. My previous postdoc was in the Indian Ocean, so it was also very different Indian Ocean air-sea interaction. So I quite like changing and learning different things. Yeah.
Thanks for the talk, Marina. Lovely stuff. You can see the wind impact from the larger scale quite clearly, and then you had this lovely plot where you had the cumulative wind anomaly and the heat flux in the channel. So it's really convincingly sort of tracking each other. And you linked it to ENSO, but also the IPO, I guess. Do you see ENSO year-to-year variability? I know your record's not very long to see it, but did you actually pick up the ENSO variability, or do you think it's more a low pass filter, sort of decadal IPO-like signal that controls that variation?
That's a really difficult question. Interesting. So there are some studies that put that El Nino into perspective, and that was a very particular one. So I think that this fits in a longer kind of variability, but that one was a very specific.
So the turn in sign of that trend was driven by the ENSO event of 2016.
Yeah. I mean,
that's the hypothesis.
Yeah. What I meant was, we see these oscillations. This is part of a bigger oscillation, but that one specifically was very punctual, was very like anomalous.
Yeah.
So I think that is quite directly associated.
Yeah, trying to understand. So when you have an El Nino, the westerly wind belt tends to move onward.
Sorry?
The south ocean westerlies
Yes.
tend to move northward during El Nino.
Yeah.
And Marina is the opposite.
Yeah.
So when the westerlies move northward, then you get a less upwelling of CTW. Then that would lead to a fuller water mass.
Normally what we see at this point.
Would you mind repeating the question? Sorry, we didn't hear that online.
Sorry. What I understand the question is that during the El Nino, you would see the wind shift offshore, and then
It will lead to instead of upwelling, you get anomalous downwelling.
You want to repeat the question? All right.
Yes, please.
So the question.
We've lost you, Fabio.
You're muted.
So can you hear now? Okay. So in the question was during El Nino years, the westerly winds moves northward. So that would lead to, I guess, colder or less upwelling of circumpolar deep water, and that colder probably varieties of CDW around the top Mars. So that's how.
Yeah. Here I'm looking at the local response to the winds, right? And I'm not showing here the atmospheric circulation, but we do see a shift. But with this shift, the eastward winds get stronger in this region at this point. So I think we were talking about maybe different scales, but at the shelf break in this region, with the shift, what we see is the strengthening of the eastward wind, or the weakening, like as Maurice was showing his work, the weakening of the westward. So that's basically what we see. And then in this case, what we are getting is the greater uplift of the CDW.
Yeah, I guess Maurice's work it shows that there's the Amundsen Sea low.
Yeah, yeah.
So it's more.
Yeah. Yeah, obviously the Amundsen Sea low plays a big role on that. So it's the combination of both. And the response is going to depend on what signal we have on the Amundsen Sea low. But during this period in this region, what we see is that moving up north and the eastward flow going stronger as a response to that shift.
Any more questions in the room? Or any question online?
Are you confused with the wind's direction?
Yeah. Right. I guess if you don't have any questions online, we're gonna close this. But thank you very much for coming, and see you next month.
Okay.
Thank you.
Yes.